Hello everyone, today we are going to learn about n-fold degeneracy. So let us begin. So here we have the Schrödinger equation written. This is the general Schrödinger equation, where psi is a function of r, and r is just like, x, y, z, to the number of dimensions of your space in some particular coordinate system, right? So today we are going to solve the Schrödinger equation for a particle in a cubical infinite square well, and we are going to evaluate the energy n-fold degeneracy of it. So to start with, let us write out the Schrödinger equation. So this is the Schrödinger equation for a particle. It's Schrödinger equation for a particle in 3 dimensions, in 3 Cartesian coordinate dimensions. Okay, and psi is a function of x, y, and z. And this equation can be quite difficult to solve in the general case. However, by making some assumptions, we can solve this pretty easily in certain cases. Now, the potential that we will be dealing with today is defined as 0 if x is between 0 and some number ax. 0 if x is between if y is between 0 and some ay, and 0 if z is between some 0 and az, and infinity otherwise. Alright, so let's actually draw out this potential to make sense of it. So here is the x, and here's the z-axis. So here we have like some ax, right? Here we'd have some ay, and here we'd have like some az. And as you guys can see, this forms some it forms like a prism, pretty much. It actually forms a rectangular prism. Okay? And inside this prism, inside of it, let's use yellow, the potential is going to be 0 inside of the prism, right? But outside of the prism, the potential is going to be infinite outside of the prism. So let's make a key here. This means infinite potential, and this means 0. So when the particle is inside of this potential, is inside the box, it has a 0 potential. And the outline of the box should be pink as well, since it doesn't include the boundary. So in the topological sense, the potential is an open ball, right? Since it doesn't, not an open ball, an open set. Since it contains all the points within except the boundary of the prism. So yeah, that's what our potential v of x looks like. So the particle can, of course, not have an infinite potential. V of x, y, z. So the particle can of course not have an infinite potential energy. So the particle is only constrained to be inside of the box. So let's go about solving this equation to find the n-fold degeneracies of the energy. So let's just copy this and paste it again. Let's copy and paste it again. Okay, so to go about solving this, we have to so we have psi of x, y, and z. Now to solve this, we are going to assume that our wave function can be separated as the product of three different wave functions, each depending on their respective variable. So this is just called separation of variables, right? We did the same thing when solving for the wave function of an n-body system, but now we're solving it for a three-dimensional system that contains only one body. So you'll actually see that the methods that we use in this video are pretty much exactly the same as the methods that we use to solve the Schrodinger equation for multiple particles, which I find kind of intriguing. So we are going to solve this for the case where x, y, and z are between ax, ay, and az respectively, which means that the potential is going to be 0. So this is our equation that we have to solve now. So let's make this substitution for psi, and we get minus h bar squared over 2m times this plus this plus this xyz equals exyz. Alright? So now what we do is if we have to distribute this inside, we get second derivative x of xyz plus second derivative of xyz with respect to y, and then do that for z, xyz, that equals exyz. Okay, so now we can take out the xyz, sorry, the yz, since they're constants once evaluated with the x derivative. Okay, this is a big X. This is the function x. This is the coordinate x, by the way. Just want to clear that up. So big X represents the actual function that is only dependent on x. Should probably draw this a bit better. And here we'd have xz, derivative of xyz plus y x derivative of z, and all of that is multiplied by minus h bar squared over 2m t equal exyz. Okay, and now what you can probably see where we're going with this. We can divide both sides by xyz, so which makes these go away, these go away, these go away, and picks up a 1 over x term, 1 over y term, and 1 over z term. This is a y, by the way. So now we have minus h bar squared over 2m times 1 over x, second derivative of big X, so it's with respect to little x, plus 1 over y, so derivative big Y, little y, plus 1 over z, big Z, little z. All this equals energy. So all of these derivatives and functions are all equal to this one constant. Okay. And now we are going to do something pretty cool. Let's separate this energy into 3 terms: epsilon A plus epsilon B plus epsilon C. Now, energy is a scalar, right? So you can separate this as a sum of 3 smaller scalars. Now, I'm not saying that E depends on A, B, C. It's not a function. It's a scalar quantity. But we can still separate it into 3 terms. So now we have minus hr squared over 2m times 1 over big X, second derivative of x, little x, plus 1 over y, little y, plus 1 over z, little z, equals epsilon A plus epsilon B plus epsilon C. So remember, E equals epsilon A plus epsilon B plus epsilon C, right? So now we can actually set this term equal to this term. We can set this term equal to this term. And we can set this term equal to this term after we, of course, distribute this term inside. Now you can do the algebra to verify this for yourself, but we can equate each of those terms to each other. So now we have three separate equations. We have that minus h bar squared over 2m is 1 over big X, second derivative of big X with respect to little x equals epsilon a minus h bar squared over 2m is 1 over big Y bump equals epsilon b. It's kind of exhausting to try all of this out, honestly. Epsilon c. Okay, so we successfully separated a three-dimensional problem into like we kind of, how do I put this? We took a three-body problem and we've separated it into three separate one-body problems. Now, technically speaking, these aren't three-body problems; they're three-dimensional problems. But you guys kind of get the analogy, the analog happening there. So what we can do now is we can multiply both sides by x, y, and z. So this makes that cross. So like that makes these all cancel out to go away. So let's erase all of this. Erase all of this. Oops, we accidentally took that with it. And these are, we have three separate problems that we can do. Now, I'm just going to analyze the y function, and we'll see that it applies pretty easily to the other functions. So let's just solve this specific equation. Minus h bar squared over 2m, second derivative of big Y, little y, equals epsilon b, big Y. So let's solve it for this case. Well, these aren't cases really, but you got the point. So what we do here is we multiply both sides by 2me over h bar squared. So we multiply both sides by minus 2m over h bar squared. So now we have minus 2m epsilon b over h bar squared y. We can then define this as k2 squared. So define this as k2 squared. And then we have second derivative of y is minus k. This is a k2 then squared y. Okay? And the general solution to this is going to be big Y of little y equals ae to the I k2x plus be to the minus I k2x. Sorry, not x. Y. I chose y because I just like the letter y. That's really the reason. So this is our general solution. Now, if you don't believe me that this solves this equation, check out my free particle video. I actually derive it pretty more explicitly. But this is our general solution. And if you didn't know, these are just equations. So if I have my y-axis over here, that looked ugly. Here's my y-axis. These are just equations for plane waves. And now we have to normalize y. And now you may be asking, well, we don't normalize y of y. We normalize psi of x, y, and z. But recall that psi of x, y, and z is just big X of x, big Y of y, big Z of z, right? So recall, so if you want to normalize this psi of x, y, and z, you would have to normalize each one of these, basically. Each one of these has to be normalized for the entire thing to be normalized. And before we normalize it, actually, we have to put in our boundary conditions. And we can also do that for each one of these. Since this has to be 0, so like psi 0, 0, 0 has to be 0, right? Which implies that each one of these has to be 0 when taking in 0 for the respective coordinate. So yeah, we can pretty much do everything on y, x, and z, and then just multiply them together to get the general big old wave function. So again, big Y of y equals a e to the I k2x plus b e times I k2x. Sorry, I keep writing x for some reason. I really mean y. So note that y of 0 has to be 0, and this equals a e to the I times 0, which is just a plus b, which means that a equals or b equals minus a. So y of y equals a e to the I k2y minus a e to minus I k2y, which equals a times, that was big times, a times e to the I k2y minus e to the minus I k2y. Alright? Now we have to actually input y of a, which would be a times e to the I k2a minus e to minus I k2a equals 0. But there's a problem. Well, here, not really a problem. We can still technically properly put in the boundary conditions for what k would have to be. But it's going to be a bit difficult if we keep using this form. So if we take this term and write it in terms of trig functions, this would be a bit more easier to solve. We could do it in the exponential form, but it's much more simple if we reduce it down to a trig function. Okay? So note that sine of u equals 1 over 2i times e to the iu minus e to the minus iu, right? That's the definition of sine. And this looks strikingly similar, like the inside term. Looks strikingly similar to this term over here. Sine of k2a would just be 1 over 2i times e to the I k2a, k2a, or sorry, we actually don't care about y right now. We just care about, we don't care about a right now. So sine of k2y, that's what I meant, k2y is just e to I k2y minus e minus I k2y, right? And that looks very, and this whole term looks very similar to what we see here, but it's not exact. So we can write this term in terms of some modified sine function. And to do that, we'd have to multiply both sides by 2i so that these terms will match. So this just equals 2i sine of k2y. So now we can sub 2i sine of k2y in here to make this much more simpler. You can see how it simplifies it a ton. Now, a is a constant, so we can absorb the 2i in there to get a prime sine of k2y. Now we still need to plug in our a boundary condition. So plugging in our a, we have that y of a equals a prime sine of k2a, which equals 0, which implies that sine of k2a equals 0, which implies that k2a equals n pi, since sine of n pi equals 0. Which means that k2 equals n pi over a, and it's also a positive integer, by the way. Well, it can be any integer, but we usually take the positive ones. And now we have quantization of k2. Now recall that from the start that k2 is the square root of 2m epsilon b over h bar, right? So from this, we can actually solve for epsilon b. You get that epsilon b equals n squared. Actually, let's rename this n to an L. This may seem arbitrary, but you'll see later. Let's rename this n to an L. Everything else applies the same. So L. It's just standard to write the y coordinate as an L instead. So epsilon beta would just be like once we actually plug in k as L pi over AY. By the way, I think I forgot to mention, but this should be AY that we plugged in instead. AY. So we get epsilon is L squared pi squared h bar squared over 2m AY. And that is our epsilon value. Similarly, we get that epsilon A equals n squared pi squared h bar squared. That's, I was reserving the n for the x case. And epsilon C is m squared pi squared h bar squared over 2m a z squared. This should be ax squared. Alright? And like, so like when we, like you can probably see this, right? When we like we solved this equation for y, but when we do, but it's like it's like almost identical to the x and z case. So we can like logically expect that we'd have the same eigenvalues, but with different quantum numbers there. So you can try it for yourself, but these are the values that you would get for x and z for those wave functions. So remember that the total wave function, the total energy is epsilon A plus epsilon B plus epsilon C. So that's just going to be equal to pi squared, which will be equal to pi squared h bar squared over 2m times n squared over ax plus L squared over ay plus m squared over az. And we see immediately that our energy depends on n, L, and m. So this equals pi squared h bar squared over 2m times n squared over ax plus L squared over ay plus m squared over az. And our total wave function, in fact, xyz, is going to be, it's going to actually depend, similarly it's going to depend, well exactly it's going to depend on n, L, and m, xyz, yz is going to equal square root of 8 over ax, ay, az of sine of n pi over ax times x, sine of L pi over a y times y, and sine of m pi over a z. Bit of a mouthful, right? If you're wondering how I got this function, like remember that y of y, we found out that it was a sine of what was it again? L pi over a y. And from normalization, we can actually normalize this. We find that a equals the square root of 2 over a y, right? And it's like literally the exact same thing for x and z of z, but like you would change your constants and your quantum numbers and your coordinate variables, and from there our general psi x, y, and z is just x times y times z, and you just plug all those in. So it's like really trivial. So I'm not going to cover it in full, but that's our wave function. That's our answer, right? Now we can finally study the degeneracies here. Now what do I mean by this? Now I want to note something that's pretty cool. Let us assume, well not assume. Let's study the case where ax equals ay equals az equals some like constant a. This corresponds to us having some box, that's literally a cube, right? So it's a literal cube. So like all the sides have equal length. All right. But note that if these sides weren't equal to each other, that would change our energies, right? Since they depend on AX, AY, and AZ. So it's kind of cool how stretching and squeezing your cube will change the energies of your particle. But let's say to the case where we all have equal length. So our energy, ENLM, would then be pi squared h bar squared over 2m a times n squared plus l squared plus m squared. Alright? So E, say E of 1, 2, 3 would be pi squared h bar squared over 2ma times 1 squared plus 2 squared plus 3 squared. And this just equals 1 plus 4, which is 5, plus 9, which is 14. Okay? And our energy is 14 pi squared h bar squared over 2ma, or just 7 pi squared h bar squared over 2ma. Okay, now that's for the case where n equals 1, l equals 2, and m equals 3. What about for the case where we switch the values? What about n equals 2, l equals 1, and m stays 3? How about for that case? Well, for that case, we'd have E of 2, 1, 3. And that's just pi squared h bar squared over 2ma times, well, now it's going to be 2 squared plus, right, plus 1 squared plus 3 squared. That's just 4 plus 1 plus 9, which is just 14. And we get 7 pi squared h bar squared over ma. Right? Sorry, this should be over ma, not over 2ma. So this is pretty cool, right? We actually flopped our quantum numbers around and we obtained the same exact energy. But remember, psi of 1, 2, 3 wouldn't actually equal psi of 2, 1, 3. Yet our energy eigenvalues as a result were the same. Isn't that not pretty strange? Let's recall that this is our psi, right? So if we were to make this, say, like 1, this is 2, this is 3, and then we just swapped them around and made this 3, this 2, and this 1 or something, our wave function would change since these depend on x, y, and z. So our wave function would actually change if we swapped around our quantum numbers. But our energy stays the same, which is really cool, right? Basically, E123 equals E132 equals E321 for AX equals AY equals AZ. However, psi 123 will not equal psi 132 and it will not equal psi 321 since they depend on X, Y, and Z. Right? It's a function, not a constant. So this is really cool because our separate eigenstates correspond to the same energy since these are all equal, right? And we call this degeneracy. When our separate functions correspond, when separate states correspond to the same eigenvalue, we call that degeneracy. And since there are three eigenvalues that correspond to different states but are equal to each other, we call that threefold degeneracy. Hence, three eigenfunctions are equal to each other. Now remember, this is only for the case where we have a cube. If our if you have like a prism that's not a perfect cube, this no longer holds. But if our particle is in some cubical box region, we have degeneracy. Okay. Now, why does this happen? Well, this happens because remember, we have n squared, l squared, m squared here. These are all being added together, right? If we have like a plus b plus c, Like, we could just rearrange that. That equals b plus a plus c. So if a was 1, b was 2, and c was 3, you could use any number you want. I'm just using 1, 2, 3. We could instead let a be 2, let b be 3, and let c be 1, and we get the same exact result, since 1 plus 2 plus 3 equals 2 plus 3 plus 1. Same thing here. We can rearrange the numbers. We can let n be some number, and then let L be what n was before, and you get the same exact energy because of the symmetry of addition. And I just find that really beautiful. It's really like cool and profound how the separate eigenstates, our eigenvalues are the same because of this cool symmetry here. Now, so threefold degeneracy occurs when when ax equals ay equals az. But what about for the case where ax equals ay but does not equal to az? Or in other words, let's say that ax equals ay but it equals, like, say, I don't know, 2.5 az, for example. Well, in that case, something a bit different happens. So ENLM is just what is it again? Pi squared h bar squared over 2m, but we'd have n squared over ax plus l squared over ay plus m squared over az. Now, know that ax equals ay, so we can just replace this with a constant a. Now, we can still flip these two around, right? We can still flip them around, since, like, they're just under addition, and they're being divided by the same number. However, we can't do the same for m, for m, right? Since m is being divided by az, and az does not equal a. So, if you want a more visual example, say I had a over 2 plus b over 2 plus, say, c over 10. Well, I can let a be 1 and b be 3. Sorry, this will be a plus. And then we have, let c be 4. We can still swap 3 and 1 here, and we get the exact same value. So we can still swap b for a, and we get the same exact number. However, we cannot swap c for a nor b, because if we did that, we'd get, like, say, 1 over 2 plus, I don't know, 4 over 2 plus 3 over 10, which isn't equal to what we had before. It's not. You can test it yourself. It's not equal to what we had before, since c is being divided by a different number. Because here we really have 1 over 2 times a plus b, then plus c. We can, of course, like, swap a and b, but we can't do the same for c. We can't just put c in here, take b outside, and say it's the same. We can't do that. So, when we let ax be ay but it's not equal to az, E123 would equal E213. We can swap these inner values, but we can't swap we can't swap them 3. We can't do that. So here we'd have twofold degeneracy, since only 2 eigenvalues would be the same for the case where ax equals ay but does not equal to az. And you can try this out for where az equals ay, but it's not equal to ax. You still have twofold degeneracy. And for the case where, like, ax is not equal to ay and does not equal to az, we have 0-fold degeneracy. So we have no degeneracy. So the highest degeneracy that we can have in this cubical box region is 3-fold degeneracy, right? Since that's when ax equals ay equals az. But when that's not always true, we have 2-fold degeneracy, and when none of the values equal each other, we just have, well, I guess you could say 1 degeneracy, but it doesn't really make any sense. We usually just say no degeneracy. So yeah, that is our n-fold degeneracies for this cubical box thing. And just it's like how much degeneracies you have. We evaluated the case where we evaluated 3-fold degeneracy, and we also evaluated 2-fold degeneracy. And we also evaluated the case we have no degeneracy. And degeneracy appears to be the addition of elements commuting, and our length of our boxes being the same. So the symmetries are what cause the degeneracies. So yeah, that's really it. I hope you guys really enjoyed this video. I surely did. And if you guys found this useful, please share it. And also one more thing, so we can take psi, of course, write it in terms of the eigenstates, and from there solve for Cn. You can do that yourself for um our for the wave functions that we solved for today, and it's gonna be pretty complicated to do it since it's like many variables there. But be my guest if you guys want to try that. You can also try solving this for multiple particles, which will like also be pretty difficult to do. Be my guest, but yeah, that's degeneracy. Hope you guys really loved this video, and I hope you guys have an amazing, splendid day. Bye.